Hey class, this is Professor Nick Sinsky at UNC Charlotte, and this is Module 3, or Part 3 of Project 1 for Computational Methods. What I'm going to be talking about today is what I might call computational adaptation, which is the process of taking the precedent study that you guys did with the parametric form and adapting it to some other kind of form. And this is really important because when you're doing your projects, you're not going to be usually creating these things out of whole cloth. They're usually going to be adapting to a wall or a site or some kind of restriction that you have that you created in Rhino first, and you need to adapt to it. Okay, a lot of the models we've been creating so far, just to get the precedent kind of figured out, have been pretty arbitrary. What you are doing may not apply in different circumstances, particularly if let's say you created something that's based on a circle or it's based on a curve, and then you end up with a straight piece. Or let's say how would it be different if it were used with a straight piece? Is that a design opportunity? Could I take a precedent that I studied and apply it to a slightly different form to extend that possibility, to explore that variation? Okay. Another thing that might be let's say you had a linear form, but you want it to extend to a curve, or you had something that was horizontal, but you want to look at it vertically. Basically, again, kind of adapting it, changing the coordinate system, changing the scale of it. How do you do that? And that's what we're going to be talking about today. Okay. And the example I'm going to be starting with is this Bernard Schuby project that was assigned. Because I think it's a good example of a couple of different things that we're going to need to learn in order to adapt our scripts. Okay. So if we go in to Rhino, I've got a box that I created. I'm going to delete this other piece here. I've got a box I created, and it's solid. I exploded it to get the surfaces, and it's not on the coordinate plane. It's actually off center. It's been rotated. Okay. And this is important because a lot of the stuff we've been doing, we've almost been kind of cheating. It's been very orthogonal, 90 degrees. This is an example of something that's at an angle. And a good question might be, how do you deal with something that occurs at an angle? And right away, an easy thing that we can do, if your process uses it, is to reference the surface directly and divide that surface. Right, so we can go into surface, divide domain, this old pattern. Okay, so trim. And if you do that, you get a parametric division of that surface that applies to the angle. The problem is that if you want to do anything with this that involves extruding from it or positioning something, you need to get a different coordinate plane. Okay, and the solution to that, to getting an object to to actually align with this that sticks out of it, is the old porcupine pattern that we discussed. And remember, to do that, take an area, get the points on the surface, or we could do a brep explode. Well, actually, what we call brep components, which actually, if you type explode, comes up. And a brep component gives you the faces and the edges and the vertices. So if you want the edge vertices, you could use a brep explode, also known as brep components, or area, which gives you the center of each of these. So that is pretty useful. Okay, we'll look at this one more later, but we'll put that in our back pocket. So we took this pattern, and we get the area to get the centroids. We do the closest point on the surface. So the points are these. The surface is the original surface. That gives us UV coordinates. We plug those into evaluate surface. And that gives us frames that we can use to do things like extrude, or in this case, position, let's say, cylinder. Okay. And the beauty of that is that it adapts to all these different surfaces without you having to invoke a particular coordinate plane when you extrude something. Okay? It only works with one surface at a time, but you get the idea. If you want to do multiple surfaces, what you can do is bake the cylinders, or bake it, and then go ahead and apply it to a new surface, and then you go ahead and bake those as well. But that pattern should be, pretty relevant to a lot of your projects. The key is just to get the right surface orientation, so that when you position things or extrude them, right? These are the normals here. If you extrude them, that you get the correct vectors of the correct planes. Okay. Let me show you another pattern here. So and actually we don't need any of this. So we got this box. Let's say that your pattern depends upon curves, like this Bernard Schumi project. A lot of the solutions I saw dealt with, creating circles, which are curves, and then moving them in a certain pattern, and then kind of shifting points. Which brings up two problems. One, what if you don't have a circle? What if you have a straight line? And two, what if how do you shift the points if without rotating this thing? You can't rotate the straight line. It doesn't work that way. So what can we do? Okay. So what I am going to show you is a little trick here. So we've got a surface, and it's still like a linear piece. And you could say, well, I could divide the surface, and I could use a contour to extract it, whatever. But I think actually an easier way to go about this, at least for right now, this is a useful pattern, is to make 2 points and make a line that connects them. And this is almost silly, but you take a point, and you can set a point by clicking an object. So if I have the endpoint selected, I can just click, and I can select another point, and that essentially gives me a line that I define manually using this so it's kind of the edge of the surface that I define. And then I can do something similar if I wanted to get the height of this, and I could just take this point and redefine it as this, and that actually gives me the edge. I don't know if you guys can see that on the video, but this edge, and this gives me the bottom edge. Then I can go through and do something like divide curve. Okay. I can also do something where I can go through and I can get the length of this line segment right here. So I find how long it is. And then I can divide that by some number. So let's just give whole numbers here. And this gives me, if I divided it 6 times, like what would I get? And the benefit of that is that I can essentially, this allows me to do things like moving a line in the Z a specific amount. So if I make a series, and if I know that this is the distance between each one, I can plug that in for n, and I plug in c as the amount, and then I actually get, so if I want to divide this up, so that's nice and parametric. Okay. If you want a line on top, then just add an extra one. So you just say c plus 1. Okay. So that's kind of a useful pattern as well. And let's actually go ahead and just move all this stuff out of the way. I don't really need it right now anyway. So, but that's a way to take a surface and allow us to make strategic copies of these. But let's go ahead and focus on this for now with the horizontal. And the pattern for this one goes something like this. you take the line and we're going to move it. Let's go ahead and steal from this amount anyway. There. And you get two matching sets of points on this. Let's go ahead and steal these two. There. Oop, wrong curve. There we go. Okay. And you've got another one. This is kind of oversimplified, but we'll go with it for now. So I'm going to go ahead and take this curve and let's multiply this amount by 2. There. So now I've got a middle and a bottom and a top. We'll go ahead and kind of space these out a bit. There's cleaner ways to do this, but this is good enough for the demonstration. Okay, and what has been done is to graft these together, let's say, so that they have a similar data structure. And then we do a little polyline. And let's go ahead and plug them in order. Okay, and you get a line between them all. And then usually we would like move these, we would like rotate these, and that would give us the twist. But we can't twist this. So what can we do? Well, what we can do is sort of slide these back and forth along this line of the plane. So how do we do that? What we can do is we can actually, instead of using a divide here, we can make a set of horizontal frames. Remember, horizontal frames go along with the angle of a line, right, of a vector. And so they are going to adapt to the angle, and they're going to allow us to perform some transformations on those points. So what I'm going to do is, this is the curve. I'm going to create a series of horizontal frames on that curve. I'm going to make the same number of frames as I had points. This might get a little confusing here. Let's get this out of the way. And then what I'm going to do, pay careful attention to this, I'm going to take a point object. And we've been playing a lot of points with putting in numbers for x, y, z. And we've kind of ignored this, but this actually says coordinate system. And a frame is a plane, right? And a plane actually can represent a different coordinate system. And if you look, let's take some of these apart here. Okay, and we'll go to wireframe. If you look at one of these things, these frames, let's go ahead and turn a bunch of this off here. Okay. A frame is a coordinate system. Look, it has a y, it has an x, it has a z, but they're angled differently. And so if you plug this in, you give that point a new coordinate system. So let's do that. Now we've got points in these coordinate systems. And now watch this. If I put a number slider in for y, it moves in this new coordinate system. But that's actually not going to work for us. We need to do actually a negative amount for this. No, what am I talking about? What I'm going to do actually is x amount. Okay, so I can move this and an x. But let's give it more of a amount here. So let's say we'll move it in 5 here. Good. Okay. And if we go through, and now we have our points, let's graph our points again. And let's turn all this on. And let's increase, well, let's Let's get our curse back too. Lots of things to turn on and off here. Okay. And then we turn on our things. Okay, so check that out. There's that, and if we play with the x-coordinate now of these local planes, you get the twist. Well, we have a problem. And the problem is a couple of things. Is that if you look at this the shape here, it actually goes outside of the form, and we don't want to do that. Like, that's not it's not legal. So what we need to do is a little bit of data structure manipulation, and this is a topic that we're going to be talking about after this project. But this is as good a time as any to start talking about it. So what we want to do is we don't want this point to factor into the equation to be moved at all. We don't want it to exist. We also don't want these points participating in drawing a line. We kind of want to like eliminate them from this. Okay. So what we're going to do is we have this list of points, 21 points, and what we can do is we can do call index. And it says remove an indexed amount from a list. So we take this list, so we take this call component and plug the list in, and you're looking for the index you want to call. And remember, the list has 21 items in it, and we want to get rid of the last one. Okay, so an easy way to do that is with another component called list length, which gives us the length of the list that we have. And if you see, this is the we have 21. Plug it in. It's going to say 21. And then what we can do is we can plug this in, and we can say I minus 1, right? Because indexes start at 0. And there you go. So we remove that last item. And actually, since these all have the same number, and in fact, if we were sneaky, we could probably just go ahead and plug in this slider, and it would work too, because we're taking 21 and subtracting 1. But this might reduce the clutter, because this thing's already plugged into a lot of other things. So either way is fine. We are going to copy paste. And I'm going to copy paste and do this. Let's go and pull these all over here. That one, and then one last. Copy the pattern here. List of points, called list, and then we plug all these in for the grafted list and check that out. Now, we would have to be careful to introduce a constraint so that we still aren't pulling away from the wall. But that works. The other thing we could do that would be almost even easier is if we were headed in the opposite direction. So if we did, say, -5, right? We would also be removing, or we would instead be removing the first one, which would be 0. So you call 0 from the list. Okay, so it's like we did with call nth, and call pattern, but now we're calling a specific item from a list. Okay, in this case again we are calling the last item, and that's getting us this pattern. And from here, the rest of it, if you've done the project, you kind of understand the logic of it. But you begin to copy these rows into a pattern and have them shift back and forth, and that would allow you to adapt it to this form. Okay. Just for the sake of argument here, let's take our inputs and change them. Yeah. See, and that works on that side then. Pretty pretty good. So it's modular, like it gets its length from the size of the cube, and from the horizontal side, we can parametrically change the number of pieces, and we can change the twist, as it were. Okay, so the thing that I'm going to be repeating throughout this lesson are that you have to pay attention to the sizes of things sometimes. Like if you can't get at the surface, extracting the size of it allows you to subdivide it, or extracting a curve from an edge allows you to subdivide it into units. And some of your projects are based on curves, so that makes a lot of sense, right? You want to find a curve from this. The other thing that's important is to work within the plane of the object, and in this case, that plane is established by these horizontal frames, and then we have a local coordinate system for this point. Okay, so keeping things in plane allows us to create some of the transforms that we want. In the next part, I'll show you that. I'm going to repeat some of this, but for a different kind of form. But this is a good method. Like this method allows us to take this form, which was circular, which was curvilinear, and apply it to a rectilinear form in a way that's adaptive and parametric. All right, I'll see you in the next part. So another pattern that we're interested in is being able to take something that we did that was a linear pattern and making it curvilinear, like making it able to adapt to any kind of arbitrary curve. And the example I have for this is, this Edakawa parking garage, or Edakawa garage club renovation. And the pattern that I showed for this to some of you was about taking a line and taking a midpoint of it and then moving it in the y-axis and then drawing a polyline across that to basically create this form that you then extrude, and that would give you these panels. And this goes to the kind of adage that I always give, which is that it's always best to try to derive something from points, and then to create lines, and then to create surfaces. That way you have the most control over it. It's very easy to control points in space. This principle kind of applies with this other project. This is a vertical element, but the idea would apply to this as well. If you were to do this over some kind of a canopy or something, so if you took what was a vertical piece and made it curve in like a vertical way, so this applies. It applies to anything like where if you had some kind of a linear element that you wanted to curve. So this might be another example where these are a bunch of straight square panels, and you would want them to adapt to a curved surface, but not to become curved, but to become like faceted. Okay, that's what this pattern comes in. It'll all be more self-explanatory when I show you. So what I've got is an arc, which is ostensibly a curve, very, very curvy. And what I'm going to do is I'm going to set that curve as a reference. And then what I'm going to do is divide the curve up. This is what's going to give me my panelization. I do a number slider with whole numbers. And let's just give it 20, give it a lot. There. So we've got endpoints and subcurves, segments. Okay. So it gives me a series of points along the curve. If I go ahead and hide this. Alright, points. What I can do with that to create a faceted effect is just make it a polyline. And to prove this, if I go back, you can see how faceted it actually is compared to the original. Okay. And that's what we want. But right now we've just got one line. So what we want to do is we want to divide it up to get at those points. So I'm going to do an explode component. And explode basically breaks this thing down into segments. So now I have 4 segments. Okay. And with those segments, I can begin doing things like extracting the endpoints, which I need. But the part that's difficult is this kind of midpoint part. Like, it's very easy for me to get the midpoint. I could just do a point point on curve. But then the problem is actually like moving it. What we did before was we would do something like move, and we do like in the y. Well, in this case, I guess I might say the x-axis because it's on the side. But if I do that, they're all going to move this way, and that's not really going to be helping me adapt to the curvature. So I need something that's going to be locally adaptive. Okay, and to do that, if you remember, horizontal frames, right, will like twist. They'll rotate to the curvature of an object, and so that's what we want. But we don't want a horizontal frames component. We want actually a horizontal frame for each one. Okay, and horizontal frame takes a curve, which I've got. Curves and lines are interchangeable. I want to remind you. A line is just a curve that doesn't have as much information. It's less curvy. Okay. So take the curve, and the t is the parameter on the curve. And in this case, actually, the parameter is the length. This is one of these things that doesn't make a whole lot of sense in Grasshopper, because usually when they say parameter, it's usually normalized from 0 to 1. In this case, they actually want a length. And so if you want to find half of the length of the curve, that's easy to do. We can do a length component, which measures the length of a curve. And you'll find that they're all the same, right? Because they've all been distributed. They've all been divided from the same curve. And we'll do a division component divided by, 2. And that gives me a frame at each of the halfway points. And the interesting thing about creating a frame, as I showed in the other example, is that a frame is a local coordinate system. So this is y, and this is x. And so if we want to move something in the negative y, that's going to give us that last point. So I'm going to go ahead and take a point object, point x, y, z. Plug in the frame for s because we are changing the coordinate system. Now the points are on there, and then if I go through and I do a number slider, I can plug it in for y. And you can see already it's beginning to move, but I want it to move in the other direction. So let's give it a maximum of 0 and a minimum of -5, let's say, for now. And there you go. Okay, so I'm going to go ahead and hide a bunch of this stuff. Clean this up a little bit. Now, to get the polylines that we need to connect these, we need the data structures to match up. This is one of these things like lofts and sweeps that we did in class, that you can't just plug all these in to a polyline and expect them to work, because the data structures are not going to match up. So if I go start, point, end, right, junk. It's not going to work. It's confusing. We're going to graph these all so that they have the same data structure. Which is this kind of ordering. All the same. And then we go polyline. Making sure that they're plugged in the right order. So start, middle, end. I'm holding shift, by the way. And there are our 4 polylines. And we go ahead and hide the rest of this as well. Well, yeah. Here's our base curve in green, and our resulting polylines in green now. And you'll notice that as I change the parameter, let's turn those points back on. Let's make it a little bit easier to see. So I turn those points back as I change the parameter. It gets more spiky. Then I can change this parameter, and then from there it's just a matter of extruding it. And doing a call on some of these. Don't forget to flatten. And then we can do our kind of pattern flipping that we were doing in an earlier version. At this point, you should kind of know how to do that. So again, if I take pretty much any weird curve, it's going to allow me to create this form locally with points and lines. Okay, so that's that pattern. Just basically builds on the ideas that we've already seen before. The real kind of magic sugar in this thing is these horizontal frames that allow us to move something in a local coordinate system, which we have to keep straight. And just data structures, right? Always going to make sure that they line up. From there, it's pretty much all the stuff we've seen before. But this will help you if you want to adapt it to a curved surface. If you're going to do something like a canopy, if you're going to change the orientation of it, what you want to make sure to pay attention to would be the coordinate plane for the point. You may need a perpendicular frame depending upon how you're modeling it. But the idea is that you need a local coordinate in order to get that offset. And that's it. I'll see you in the next part. So for this last pattern, I'm going to talk about something called a morph box. And what this allows us to do is take some arbitrary geometry and morph it according to sort of like a tile pattern. And there's different uses for this, but mostly what we see is some kind of an object that fits within a square box. It doesn't have to be exactly like a rectangle or a square. It could be like a donut or a sphere or something, but that fits into a bounding box that's basically like rectangular. Okay, and what I've got here in this sketch are two patterns that we've seen before. I've got a surface that I created based on a curve. So I take the curve and I extrude it, and then I subdivide it. Right, this is all pretty common stuff. And then the other thing that I did was I have a parametric object that I made that's a rectangle. You got your domain that's feeding it. It's actually a square because I'm using the same domain for x and y. Then I have this other thing where I have a polygon, and I can control the number of sides that it has. And the radius of the polygon is basically the dimensions of the rectangle divided by 1.5. Okay, so a little bigger than half. Okay, like 3 halves. And the other thing that's different about this, though, that I need to call your attention to is this planar surface. So what a planar surface is that if you have curves that are in a plane, it will create a surface out of them. And if you plug in, two curves, my rectangle and my polygon, then you can get holes in your planar surface. And then, of course, when you extrude a surface, you get a solid. And that's how I created this parametric base geometry here that we're going to morph. Okay, so I can control these dimensions of it. So it's very parametric. Okay, the box morph works with any geometry. So it could be some geometry that I draw. So it actually could be a torus, our old friend, the donut. Could be a torus, okay, or something that you drew. But the idea is it should fit into kind of a box in some fashion. And if it doesn't, it'll get stretched. And again, this is good for taking some geometry, like some of the systems that you guys created in your project, and adapting it over any kind of surface that you can get your hands on, and that you can tile up. Okay, so I can control the tiling here. Okay, so we're gonna go ahead and put a morph box in. Actually, box morph. Okay, box morph takes geometry, takes a reference box, and it takes a target box. So the reference is basically a reference to the size of the geometry, and then the target are where the geometry is going to go. So it's kind of like an orient component, something we've seen before. Only morph is going to take the size of this box and stretch this geometry to whatever the target box is. And that'll be pretty clear what that is in a second here. So what I'm going to do is I'm going to put a container for my geometry. And actually my geometry is this, but I'm just going to put it in there anyway so we can tell what it is. So geometry goes into morph. And then what we need is a bounding box, because we need to know what size this box is. And this is pretty dumb because this is kind of already a box, but the bounding box is just an easy way to get those dimensions, and it works for pretty much like any geometry. So if I put in a bounding box, that's what I get. I actually get, I'm going to turn this off here, turn a bunch of these off. I get a box, okay. And then the last, and then I need to pipe that into the reference box. And then the last bit is I take my surface, and I'm going to do something called a surface box. And what a surface box is that it basically extrudes boxes from the shape of a surface, and that'll be clear in a second. So I take the surface, actually, I take the base surface. This kind of works like this, like divide domain thing does with the subsurface. I can take the domain here, the domain goes into the domain here, and you can see it's already happening, right? And then lastly, I'm going to put in a number slider for the height of the extrusion. And in fact, actually with this pattern, I'm not even sure I need this subsurface anymore. Okay, so then I can control this, and those are my boxes. So I take my twisted box output and import it to the morph, and this is going to crunch a little bit on your computer. It is pretty computationally intensive. Whew, look at that. So again, it morphs. Like, these things are kind of changing. They're kind of changing shape. I want to caution you, this works really well, but A, it's very slow on your computer. It does not update like very fast, so you have to be very careful about what you plug into it. B, it is not the best way to solve a lot of your problems with your projects. Like, the best way to do something to make a geometry parametric across any surface is to basically construct it using points and lines and planes and different kinds of topological stuff that we've talked about. The morph box is kind of a last-ditch thing. It always works, but it's not very excuse me. It's not as powerful, and it's not as clean and as fast as building it yourself from points and lines and planes and things. Okay, but for some of your projects, like, nothing else is going to work. So I do want you to understand how this works. It's great for prototyping. Looks great. Okay, so if I go back, remember my geometry is parametric, so if I go back, now changing the size of the geometry is not really going to matter because the whole thing's just going to morph anyway. But if I would do something like changing the polygon, that is going to change the geometry. So now I've got, pentagons, and I've got hexagons, okay? And if I changed the radius of it to something else, that would also propagate and change the form. And it takes a little bit. There you go. But that's the morph box. Pretty effective across different surfaces. Works with a range of geometry. Just for giggles, I'm going to go ahead and reference this as my geometry. So I'm going to go ahead and disconnect that, and go ahead and click on my geometry here. And again, it's going to be a little sluggish. Got to make the donuts. Whew. That is taking a while. There we go. So it took a while, but there you go. Neatly, divided into these donuts. Like I said, pretty powerful, very slow. I actually paused the video and restarted it again because it took my computer so long. So be careful with that. But it does work pretty effectively in a lot of situations, and it may be the only thing that works for you. Okay, so that's a morph box. Go ahead and work on these for Thursday's lab, that's next Thursday. Bear in mind that this week there is no class Thursday and Friday. But work on this with your group. Come up with something that works aesthetically well, that maps your project precedent to the pavilion that we discussed. Okay? And bring that stuff into lab on Thursday. I will try to answer your questions in class and kind of help you out. And then on that Friday, the day after, I would like to see your submission, like your in progress like submission for this project. Okay? Good luck. I'll see you soon.